Hey, sorry about this, but this one's going to be a little bit longer than normal. So, conservative forces and mechanical energy. It's an important concept. We got to take our time and get it right here. Okay. So, in addition to kinetic energy we talked about last time, objects can also have what we call potential energy. And we're going to abbreviate, unfortunately, with the letter U. I'm not sure why, but U means potential energy. So, the best way to think of potential energy is it is the energy of position. Objects can be in a high energy position, like a boulder on a cliff, or they can be in a low energy position, like a boulder at the bottom of a cliff. If you think about it, you're not uncomfortable standing next to this boulder here because you know what? It doesn't have much energy and it's not going to develop kinetic energy and smash your head in. But if you're standing at the bottom of this cliff, you're going to be a little bit nervous because you understand that's in a high energy position and it could convert that potential energy into kinetic energy and smash your head in. Honestly, that's why things up high scare us. Okay. So, how do you determine how much potential energy an object has? Well, you do it by using the work equation. So, if you think about it, I have an object of mass m that's at the bottom of a ledge. Okay. The amount of work needed to lift it is going to equal to the weight of the object. The mg of the object is the force I have to apply, and h is the height I'm going to lift it. That's the a distance I'm going to move it. So, work is going to equal to mgh because this is the force and this is the distance. So we'd use the general form then for gravitational potential energy. U for potential energy and lowercase g, meaning gravitational, is going to equal mg times the change in the object's height. So mg delta h, that's going to be our standard definition, our equation for gravitational potential energy. Now, one thing about gravitational potential energy that's weird is that you have to decide where you want to say the object has no potential energy because honestly, they always have potential energy. It's just a question of what you want to say is the 0 point. So, for instance, I have an object on a table and I have an object 2 meters above the table. How much potential energy does it have in each of these positions? Well, it depends. So, maybe I want to say the floor is where it has zero potential energy. So, I say, well, on the table, it was a meter above the floor, so it had 20 joules worth of energy because 2 times 10 times 1. And when I lifted it a meter above the table, now it's 2 meters high, so it has 40 joules, 2 times 10 times 2. But you may say, no, 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 no. You know what? On the table, it doesn't have any potential energy. I'm only interested in how much energy it has above. I'm going to say it has 0 on the table. And so therefore, when I lift it a meter above the table, it has 2 times 10 times 1. Both cases is true. Do I want to make the floor equal to 0? Do I want to make this table equal to 0? It's totally up to me which I want to decide. Okay, and it actually helps us solve problems. Okay, now we often think of potential energy as stored energy, and here's why. So I have this object on the ground, it's got 0 potential energy. I'm defining the ground as 0. Now, it's a 5 kilogram object, 2 meters in the air, so 5 times 10 times 2, it just gained 100 joules worth of gravitational potential energy when I set it on the top of this little ledge. And then you know what? I walk away from it, and it stays there for years. That 100 joules is still in it even years later. It didn't go away. So you can think of the energy that I put into it, that energy in my body was converted into energy in the form of potential gravitational energy, and it stays there. All right, we call it stored energy. Now, what happens is years later that can be released and reconverted back into kinetic energy. 20 years later, it still has 100 joules worth of. Now I give it a little bit of a nudge and it starts to fall to the ground. Now watch what happens. It's halfway to the ground. If it's halfway to the ground, it's only got half as much potential. It's got 50 joules worth of energy. It turns out you can't create or destroy energy. It's called the first law of thermodynamics. Where did the energy go? Well, it got converted into kinetic energy. The object is now moving faster, so it has 50 joules worth of kinetic energy, and the moment before it hits the ground, it's just a molecule away from the ground. It doesn't have any potential energy anymore. All that energy has been converted into kinetic. It's got 100 joules worth of kinetic. So the amount of work I put into it comes back out as kinetic. And then when it hits the ground, it gets turned into thermal and other forms of energy. Now, there are several forms of potential energy that we could concern ourselves with, but in AP Physics 1, we're only going to concern ourselves with two. We're going to worry about gravitational potential energy and spring potential energy. So spring potential energy will denote with U subscript S. Think of it this way. I have a spring that hasn't been compressed. I have this block of wood, let's just say, okay? Now, right now, there's zero energy in the spring. Well, I'm going to do some work. I'm going to push this block into that spring, and I'm going to apply enough force across enough distance to do 50 joules worth of work. And then a little latch clicks, and I hold it in position. This spring now has 50 joules worth of energy in it. So I say it has 50 joules worth of spring potential energy. And again, I could leave it there for years. But as soon as I pull that little block out of the way, then what happens is that spring is going to push this object forward, and the energy in here is going to go to zero. But all that energy is now going to be transferred into this object, which is now going to have 50 joules worth of kinetic energy in it. So you see, what we end up with is potential energy gets converted to kinetic and vice versa. And that's really what today's lesson is all about. Now, when an object can have potential energy, we say that the force that was being applied then must be what we call a conservative force. So a conservative force is one in which the work done by that force can later be fully reconverted back into kinetic energy. So it can be, we say, recovered completely as kinetic energy. So this is true with gravity, with gravitational force and spring force. So the work done lifting this against gravity can later be reconverted back into kinetic energy. The work done compressing the spring can later be reconverted back into kinetic energy. So we'd say gravitational force and spring force are conservative forces, right? Where the energy can be converted or back into kinetic energy. Now, there's several conservative forces we could talk about. There's gravitation, spring. There's also magnetic. We'll see that later on in the year when we deal with collisions, and electrostatic. So these are the ones where we can have it, but basically, a conservative force is one where it produces these forces cause changes in the potential energy of a system, and we're only going to concern ourselves with gravitational and spring. So, in order to gain potential energy, work must be done against a conservative force, and also, and this is an important one, and a little bit of a pain in the butt, but we got to get used to it. Potential energy is only considered to be present when both of the objects between which that conservative force is established are part of the system being considered. I'm going to say it again. The potential energy can only be considered to be present if both of the objects involved in the conservative force are present. So let's take a look at gravitational force, okay? So if the system I'm considering is called the Earth rock system, the force of gravity, the conservative force here, is between the Earth and the object. So therefore, the object can have gravitational potential energy. So if I lifted this object 2 meters and gave it 100 joules, it did 100 joules worth of work, it has 100 joules worth of gravitational potential energy, and as I release that, 100 joules worth of gravitational potential energy is going to be converted into 100 joules worth of kinetic energy. But if the Earth isn't part of the system, I just have an object on a cliff, then instead of saying it has potential energy, I would say that as it falls, gravity is an external force. It's not part of the system. So an external force acted on it, causing it to gain 100 joules worth of kinetic energy. Now, it might seem like a kind of silly, arbitrary thing to worry about, but it turns out it's one of the things that College Board is going to test you on quite a bit. You've really got to be careful to see which objects are in the system and which objects are not in the system, because it leads to a concept called conservation of mechanical energy. So mechanical energy is just the sum total of all the kinetic and potential energies that are part of our system. So we can have kinetic energy, we can have gravitational potential, we can have spring potential energy. So let's look at this system here. This system consists of a block that is moving to the left, and it has 100 joules worth of kinetic energy. See these lines? That means it's moving. This object is moving. It has kinetic energy. It's compressed to spring. That spring has spring potential energy. I have a block spring system. So how much energy does it have? Now there's no change in height, so I can ignore the gravity here, as there's no gravitational potential energy. So I have zero gravitational potential energy, but I have 100 joules worth of kinetic energy, 50 joules worth of spring potential energy. The mechanical energy of the system is 150 joules. Let's look at this one here. In this case, I have an object that is moving upwards. See that? It's moving upwards. It has 200 joules worth of kinetic energy. It's at a height such that it has 100 joules of gravitational potential energy here. So in this case, the system is a rock Earth system. So the mechanical energy is 100 plus 200. It has 300 joules worth of mechanical energy. And this is important because we want to solve problems using what we call the conservation of mechanical energy. Now, conservation laws are ones in which we simply whatever we start with is what we end with. That the total sum of what we start with is equal to total sum of what we end with. And we're going to look at a number of these conservation laws this year. So we're going to start off with conservation of mechanical energy. So when only conservative forces act on a system, then the total kinetic and potential energy of the system stays constant, while the different parts of it will change. So I might gain kinetic energy and lose potential energy, but the total ME is going to stay the same. So the initial ME of the system, so the KE plus U that I start with, is equal to the KE plus U that I end with. So let's just take a look at this. Here I have a rock earth spring system. So uh, to start off with, my initial conditions are this. Initially, what I have is this, that the kinetic energy is 200 joules. The gravitational potential energy is 100 joules because it can still fall. The spring has no energy in it, so the spring potential energy is zero. So if I sum up my mechanical energy to start with, my initial mechanical energy is going to end up being U plus K plus US, 100 plus 200 plus zero. I have 300 joules worth of mechanical energy to start with. And since these are conservative forces, and both the Earth, the rock, and all three objects, the Earth, the rock, and the spring, are all part of the system, therefore, what's going to happen is this: my final mechanical energy has to equal my initial. So the rock hits the spring and it slows down. So what happens is it now, as closer to the ground, it only has 50 joules worth of gravitational potential energy because it's moved closer. The spring is pushing against it, so it's slowed down. Instead of having 200 joules worth of kinetic energy, now it's only got 150 joules worth of kinetic energy. Well, that means that I must have 100 joules worth of spring potential energy, because the total is going to be 50 plus 150 plus 100 is 300 joules. That's the same amount I started with. Since the spring and gravity are both conservative forces, the law of conservation of mechanical energy applies. The amount of energy I started with is equal to the amount of mechanical energy I end with. Now, if the system is defined to be the rock earth system, mechanical energy is not going to be conserved because I have another force that's not part of my system, and it's going to do external work on the system. So I'm getting a little bit ahead of myself, but let's just try this. Same thing as I had before. So my initial mechanical energy is going to be gravitational plus kinetic, which is 100 plus 200. I have 300 joules of mechanical energy. Now the Earth and the rock are part of my system, but the spring is not considered to be part of the system. So therefore, the work done by the spring is going to be external to the system. So now this came down lower, so it's only got 50 joules worth of gravitational potential energy. It's slowed down. Now it only has 150 joules worth of kinetic energy. The mechanical energy of my system is now just going to be 200 joules. The mechanical energy went from 300 to 200. Why? Because the spring did 100 joules worth of negative work on the system. It wasn't part of the system. So I can't consider it to be part of my mechanical energy. Seems kind of frustrating, but you do have to be careful when you're reading prompts on the test to see what is and what isn't part of the system. Now, one thing about conservative forces is that uh, the path taken is irrelevant to the change in the potential energy of the object. So the energy change depends only on the initial and final position, not the path taken. So if I lift this object straight up, it gained uh, a certain amount, let's just say 100 joules. All right, if I took it this path here, I went up higher and came back down, well, it still gained 100 joules worth of potential energy. I lowered it down and then lifted it up to here, it still gained 100 joules. It doesn't matter what path I take. All that matters is where I start and where I end. That seems kind of trivial, but it's actually pretty powerful. Look at this. I have an object. It's here. It's got potential energy. It doesn't have any kinetic energy. I let it fall. Well, what happens? If I have a block Earth system, what's going to happen is it's going to convert its potential energy into kinetic energy, and it's going to end up with 100 joules of kinetic energy when it reaches the ground. Watch this, though. I put it here. Now, this is a frictionless surface, so there's no external work being done here. All right, we'll talk about non-conservative forces later. But here's the deal. The path doesn't matter. It doesn't have to move straight down. So what happens is it's the same height here as it was here. And so, I didn't mean to do that. So what happens is as it slides down here, what's going to happen is when it gets to the bottom, it no longer has any gravitational potential energy. So all of that's got converted into kinetic energy, it has 100 joules, even though it went a different path. It didn't go straight down. That's pretty powerful. It doesn't matter which path it takes. At the end of the day, all that matters is its initial and final positions. It was initially here and it ended up here. The same change in height equals the same change in kinetic energy. So College Board loves to present you with things like this. This object is going to fall straight down. This one is going to follow this curved path, right? So which one's going to reach the ground first? Well, clearly this one went a shorter distance. It was accelerating at a higher rate the whole time. So clearly this one's going to get to the ground first. But what about which one is going faster when it reaches the ground? It turns out because this is a frictionless surface and we have a conservative force, gravitation, acting between this object and the ground, that the path taken is irrelevant. At the end of it, they both started off with the same amount of potential energy and they lost all of it, so it must have all got it converted to kinetic energy. They both have the same velocity upon reaching the ground. Even though this one got there first, still, because we conserved mechanical energy, all the potential energy got converted to kinetic energy. In both cases, they're going the same speed. All right, well, let's just try using this to solve something a little bit more quantitative. Okay, I have this object. It's sliding up a frictionless incline. It's 2 meters above the ground. It's traveling 5 meters per second. Has a mass of 4 kilograms. So what I want to know is how far above the ground will this object go before it finally stops? I'm going to solve this using conservation mechanical energy. I'm going to say the mechanical energy I start with is the mechanical energy I'll end with because I only have conservative forces, and therefore conservation mechanical energy applies. So, what I started with was I have gravitational potential energy, I have kinetic energy because it's moving, and at the end, I'm going to say the gravitational potential energy plus the kinetic energy is going to equal what it was to start with. But here's the thing: at the end, this object is not moving, so this velocity is going to be zero, so that goes away. So what I say then is I have 4 kilograms. Gravity is 10, it's 2 meters up, so that gives me 80 joules. Plus I have 5 meters per second squared times half of 4, that gives me another 50. Uh, and then I'm going to solve it for h, and I'm going to come with 3.25 meters. All right, so the thing to keep in mind here is when it stops, it's got no kinetic energy. What if I said instead, well, how far above the ground is it going to be when it only has 3 meters per second of velocity? Well, I'm going to do the exact same thing I did before. I'm going to say a conservation of mechanical energy applies as long as this is a frictionless surface. Uh, I'm going to do the same thing. I'm going to say the sum of the potential energy and kinetic energy initial is going to be equal to the sum of the potential energy plus kinetic energy afterwards. But in this case, this is non-zero because it's 3 meters per second. But other than that, the same thing applies. I just substitute in the values. I solve for the unknown height, and I'm going to come up with 2.8 meters. All right, last thing. I promise we're going to be done here. Okay, energy bar charts. Energy bar charts are a pretty uh, uh, good way of visualizing energy. So the idea here is it's a zero sum game when I have conservation, right? So the total mechanical energy I have before is the total mechanical energy I have afterwards, as long as I only have conservative forces applying. So imagine I have an object that is falling down. It's got gravitational potential energy, it's got kinetic energy, and there's a spring. So there's spring energy. And we're going to say this is a block earth spring system. So all the objects are involved here. Okay. So in that case, let's just say this object starts off, it's got 300 joules worth of kinetic energy. It's got 400 joules worth of gravitational potential energy. The total, it doesn't have any joules worth of spring potential energy. 400 plus 300, the mechanical energy I start with is 700 joules. The idea is conservation mechanical energy tells me that at the end, it still has to have 700 joules worth of mechanical energy. So if in the course of falling, uh, it reduced its gravitational potential energy to 200. The spring slowed this down, so now it only has 200 joules worth of kinetic energy. The sum of those two is 400. Since I can't lose any and I have to have 700, the spring potential energy must equal 300, so that when I add all these up, I still have mechanical energy at the beginning is 700. So at the end, it must also be 700. One more and we'll be done. Okay. Let me move my face out of the way here. Okay, so here's what we've got now. We got a rock moving up. It has 150 joules worth of gravitational potential energy. It has 400 joules worth of kinetic energy. Ignore that. It's a little boo-boo here. It's got 400 joules worth of kinetic energy. So therefore, the total mechanical energy to start with is going to be 150 plus 400. That's 550 joules worth of mechanical energy. How much kinetic energy will it have when the rock is twice as high above the ground? Well, if it's twice as high, mgh, h doubles, so it has twice as much potential energy. So instead of having 150, it's going to have 300 joules worth of gravitational potential energy. The total isn't going to change. So if I had 550 mechanical energy before, I have 550 now. So therefore, how much kinetic energy must it have? Well, how much do I have to add to 300 to get to 550? I have to add 250. So this went from 400 down to 250. It's just an easy way of solving. So listen, I know this is a long one. Thanks for watching. I'll try to make